Hello viewers, in today's session we are going to discuss another important problem from integrals, and here we are going to evaluate this integral from 0 to 2a, and the integrand is x cube times square root of 2ax minus x square, right? So here let us call this integral as I, and in order to evaluate this integral we'll first make use of the method of substitution to reduce this integral into beta function, and then we'll apply some properties of beta and gamma functions to get the final value of this integral I, right? So let us first write this integrand as here we have x cube and square root, that is 2ax minus x square raised to half. So we can write this integrand in this form. Now if we take x common from 2ax minus x square, then we have x cube, and here we have x raised to half taking x common, and here we have 2a minus x raised to half. So now we can add here these two exponents. So we have 3 plus half, that is 7 over 2. So here we have 7 over 2 and 2a minus x raised to half. So now we can write this integral I in this form, that is x raised to 7 over 2, and square root, or we can write here 2a minus x raised to half and dx, right? So now let us make the substitution here, that is x is equal to 2at, right? And here we can also make trigonometric substitution also, but here I will prefer this one. So x is equal to 2at, so that dx over dt is now equal to d by dt of 2at, and this is 2a times the derivative of t with respect to t, that is simply 2a. The derivative of t with respect to t is 1. So we can now write dx is equal to 2a dt. Now let us change the limits. So here the lower limit is 0 and the upper limit is 2a. Now the corresponding values of t can be obtained from this relation. So t is x over 2a. So when we take x is equal to 0 over here, then the value of t is 0 over 2a, that is simply 0. And when we take x is equal to 2a, then the value of t is 2a over 2a, that is equal to 1, right? So now let us write this integral I in terms of t. So now the limits of integration goes from 0 to 1, and here we have x raised to 7 over 2. So x is 2at raised to, here we have 7 over 2, and then we have 2a minus 2at, because x is 2at, and here we have half, and dx can be replaced by 2a, and here we have dt. So now we can write 0 to 1, and here we can write 2a raised to 7 over 2 and t raised to 7 over 2, and here we can take 2a common. So we have 2a raised to half, and we have 1 minus t raised to half, and here we have 2a dt. So we can now write 2a raised to 1, and here we have dt. So now we have 2a raised to 7 over 2, 2a raised to half, and 2a raised to 1. So we can now take all these three terms outside the integral, and we can add the exponents by using the laws of exponents, because here the bases are same. So we have 7 over 2 plus half plus 1, right? And here we have 0 to 1 and t raised to 7 over 2, and 1 minus t raised to half, and here we have dt. So now this is 7 plus 1, 8. 8 over 2 is 4. 4 plus 1 is 5. So we have 2a raised to 5. And here we have 0 to 1. And t raised to 7 over 2 can be written as t raised to 9 by 2 minus 1. Right? Because now we are going to change this integral into beta function. Right? And here we can write that is 1 minus t raised to half as 3 by 2 minus 1. So now we can write here 2 raised to 5 is 32, and here we have a raised to 5, and this is 0 to 1, t raised to 9 over 2 minus 1, 1 minus t raised to 3 by 2 minus 1 dt. So now the beta function is defined as beta m comma n, and we have the integral that is 0 to 1 and t raised to m minus 1, 1 minus t raised to n minus 1 dt, where m and n are greater than 0. So now if we compare this integral with this one, then here we have 0 to 1, 0 to 1, and t raised to 9 by 2 minus 1, 1 minus t raised to 3 by 2 minus 1. So the value of m is equal to 9 over 2, and the value of n is 3 over 2, and both m and n are greater than 0. Right? So now the integral I can now be represented as 32a raised to 5, and here we have the beta function, that is beta m comma n, and we have 9 by 2 comma 3 by 2. So now to get the value of this expression, we have to make use of the relationship between beta function and gamma function. And we know that beta m comma n is given by gamma m times gamma n divided by gamma m plus n. So here we have now I is equal to 32 a raised to 5, and here we have gamma 9 over 2, then we have gamma 3 over 2, and gamma m plus n. So 9 by 2 plus 3 over 2 is 9 plus 3 is 12. 12 over 2 is 6. So here we have 6. So now we have to evaluate this expression. So now to get the value of this expression, we have to make use of these two important results, that is gamma n plus 1 is given by n times gamma n, and gamma n plus 1 can be written as n factorial, right? So here we have gamma 6. So gamma 6 can be evaluated by using this result. We can now write 6 as 5 plus 1. So here we have 5 factorial, that is 5 times 4 times 3 times 2 times 1, and that is equal to this is 20, 60 and 120, right? And here to get the value of gamma 3 over 2, we can use this relation. So we can now write gamma 3 over 2 as half plus 1. So now the value of n is half, so we have half times gamma half, and the value of gamma half is equal to square root of pi. So we have half times square root of pi. Now the value of gamma 9 over 2 can be calculated by using this result. So we have gamma 7 over 2 plus 1. So we can split 9 over 2 as 7 over 2 plus 1. So now we have here 7 over 2 times gamma 7 over 2. So now we can again apply the same result to gamma 7 over 2. So we have 5 over 2 plus 1. So this is 7 over 2 times 5 over 2 times gamma 5 over 2. So now we have 7 over 2 times 5 over 2, and gamma 5 over 2 can be obtained again by using this result. We have gamma 3 by 2 plus 1. So this is 7 over 2 times 5 over 2 times 3 by 2 times gamma 3 over 2. Now gamma 3 over 2 is half times square root of pi. So we have 7 over 2, 5 over 2, 3 over 2, and half square root of pi. So here we have 7 times 5 is 35, times 3 is 105, and here we have square root of pi divided by this is 16, right? So now let us substitute the values of gamma 9 over 2, gamma 3 over 2, and gamma 6 as 120 in this expression. So now we can write here 32 a raised to 5, and here we have 105 over 16 times square root of pi, and here we have half times square root of pi divided by gamma 6, that is 120. So now we can simplify this expression. So we have here 16 times 2 is 32. So here these terms get cancelled, and here we have a raised to 5, and square root of pi times square root of pi is pi. So we have here pi times a raised to 5, and here we have 105 over 120, right? So let us simplify this term. So we have here 5 times 2 is 10, this is 1. This is 5 times 2 is 10, this is 4. And here we have 3 times 7 is 21, and 3 times 8 is 24. So now we have 7 pi over 8, and here we have a raised to 5, right? So the value of this integral is given by 7 pi over 8 times a raised to 5. So viewers, this is how by the application of beta and gamma functions we can easily evaluate integrals of these types. So now here we can make an important deduction by taking a special value of a. Suppose we take a is equal to 1, right? Then we have this integral that is 0 to 2, because we are taking a is equal to 1. So 2 times 1 is 2. Here we have x cube, and square root of 2ax minus x square. So a is 1. So here we have simply 2x minus x square and dx. Now the value of this integral can be obtained by replacing a by 1 in this expression. So we have 7 pi over 8 times 1 raised to 5, and this is 1. So we have simply 7 pi over 8 times 1, that is equal to 7 pi over 8. So the value of this integral is equal to 7 pi over 8. Hello viewers, in today's session we are going to discuss another problem from integration, and in this session we are going to evaluate this integral, that is 0 to 1 x raised to a minus 1 minus x raised to b minus 1 divided by natural log of x, right? So here we are going to make use of the method of differentiation under the sign of integration, right? So in this method what we do, we treat any of these two constants, that is a and b, as a variable, right? So here we can select either a or b as a variable, and the rest of the terms may be considered as constants, right? And then we differentiate this integral with respect to the selected variable. So let us call this integral as I, right? And here we select a as a variable, and the other terms may be considered as constants, right? So we'll differentiate partially with respect to a, both sides, right? So here we can now write di over dA. So we'll differentiate this integral I with respect to a. So here we write this operator, that is del over del a, and here we have the integral 0 to 1, and we can write the integrand as x raised to a minus 1 over natural log of x minus x raised to b minus 1 over natural log of x. And here we are treating a as a variable and b and x as a constant. So we'll differentiate this term which is inside the integral sign, that is our integrand, with respect to a. So now taking this operator inside the integral sign, we have now a 0 to 1, and we have del over del a of x raised to a minus 1 over a natural log of x, and the partial derivative of this term with respect to a is 0, because we are differentiating this integrand with respect to a partially, right? And here we have dx, right? So now here 1 over natural log of x may be considered as a constant. So we can now write 0 to 1, 1 over natural log of x, and we have del over del a of x raised to a minus 1, and here we have dx. So now we have a di over dA as this term. So now let us find out the derivative of x raised to a minus 1 with respect to a. So now let us separately find out the derivative here. So we can now write here x raised to a minus 1, and we can write x raised to a minus 1 as e raised to natural log of x raised to a minus 1, because we know this important result, that is e raised to natural log of say p is equal to p. So here our p is x raised to a minus 1, right? Okay, so now here we can now apply the properties of log, that is a log of say m raised to n is n log m. So here we have a minus 1, so we can take a minus 1 in front of the log notation. So we have a minus 1 and natural log of x, right? So now let us find out the derivative of e raised to a minus 1 natural log of x with respect to a. So we have here e raised to a minus 1 natural log of x, because the derivative of the exponential function is the exponential function itself. And then by chain rule, the derivative of a minus 1 times natural log of x with respect to a is simply a 1 minus 0, and here we have natural log of x, because the derivative of a with respect to a is 1, and the derivative of 1 with respect to a being a constant is 0, right? So we have simply here e raised to a minus 1 times natural log of x can be written as simply this term, that is x raised to a minus 1. So we can now write again natural log of x raised to a minus 1, and here we have natural log of x, and this term is simply x raised to a minus 1 times natural log of x. So now we can write here 0 to 1, 1 over a natural log of x, and the derivative of x raised to a minus 1 with respect to a is given by x raised to a minus 1 natural log of x, and here we have dx. Now these two terms get cancelled and we have simply 0 to 1, x raised to a minus 1, and dx, right? So now again we can treat x as a variable, and we can use this well-known result, that is integral x raised to n dx is x raised to n plus 1 over n plus 1, right? So here for n we have a minus 1, so we have x raised to a minus 1 plus 1 over a minus 1 plus 1, and the limits of integration are from 0 to 1. So we have now x raised to a, and here we have simply a, and we have the limits from 0 to 1. So now we can substitute the limits, and we'll take the difference. So we have now 1 over a. First we'll take x is equal to 1, so this is 1 raised to a is simply 1, and here we take x is equal to 0, so this term is now 0. So we have simply 1 over a, right? So now the derivative of this integral I with respect to a is given by di over dA is equal to 1 over a. Now this is a variable separable form of differential equation, and we can solve this differential equation by a method of separating the variables. So we can now write di is equal to dA over a, and now integrating both sides, and c is the constant of integration. So here we have simply I, and here we have the integral of dA over a is natural log of a, because we know that integral dx over x is natural log of x, right? And here c is the constant of integration. So now we have this condition or this equation where I is equal to natural log of a plus c. Now we have to find the value of this constant of integration by using or by imposing some condition on this integral I. So now let us make use of this condition, that is a is equal to b, and taking a is equal to b in this integral, we have I is equal to 0 to 1, and we have x raised to b minus 1 because we are taking a is equal to b, and here we have x raised to b minus 1 over natural log of x and dx, and now these two terms get cancelled, so here we have 0. So the integrand is now equal to 0, so the value of this integral reduces to 0. So now we have this condition, that is when a is equal to b, then the value of I is equal to 0. So now let us make use of this condition to get the value of c. So here taking a is equal to b, we have now I is equal to 0. So we have I is equal to 0, and that is equal to natural log of b plus c, taking a is equal to b. So now solving this equation, that is 0 is equal to natural log of b plus c, we have c is equal to a negative of natural log of b, right? So the constant of integration c is equal to negative of natural log of b, and substituting this value in this equation, now I is equal to natural log of a minus a natural log of b, and using the laws of logarithms, here we have log of a over b, right? So the value of this integral I is given by natural log of a over b. So viewers, this is how, by making use of the concept of differentiation under the sign of integration, we can easily find out the values of these kind of integrals.